Okay, so we're going to be focusing on Lesson 1, Assignment 2, which is forces, and Lesson 1, Assignment 3, which is motion in a circle and the centripetal forces that cause that. Right, so Assignment 2 is about forces. So forces are energy that can be used to cause changes in motion. So forces can be a push or a pull, either way. And we can think about forces as being contact or non-contact forces. So contact force would be if two things are actually touching and one is applying energy directly to another. So if you throw a ball or you pick up an object, you're directly putting force on it. A non-contact force would be something like gravity. So the Earth is going around the sun and the sun's gravity is pulling on Earth, but it's not actually touching it. Okay? Or if you stand at the top of the steps and you drop something down, Earth's gravity is pulling the object down, but they don't actually touch. So that's a non-contact force. So when we talk about forces, we start with Newton's laws. They're going to be how forces affect motion. So the first law of motion is that bodies at rest tend to stay at rest, and bodies in motion stay at motion at a constant velocity. And to make this change, you need an external force that's unbalanced. Okay? The idea that the objects keep doing what they were doing is called inertia. So if you have an object just sitting there, so there's a chair just sitting on your floor, it's not going to move unless you put forces on it. Okay, it's just not going to start spontaneously moving. The chair has inertia. It doesn't want to go anywhere. Also, moving things have inertia. They don't want to change their motion. They're going to keep going until an unbalanced force stops them. Inertia is also based on mass. Things with more mass have more inertia. Their motion is harder to change. Okay, so something with a small amount of mass, like this guy, it's going to be more easy to make a change. Just a small amount of force will send it rolling along. Where something with a large amount of mass, like this guy over here, that's going to take a lot more force to make a change in its motion. Okay, so that's how inertia works. Okay, so you might say, well, wait a minute. You just told me objects in motion stay in motion at a constant velocity, but that's not what I see. So when I see things on Earth, they don't stay in motion forever. Okay, if I roll a ball across the floor, it's going to slow to a stop. If I push an object across the floor, it's going to slow to a stop. Oh, if a car runs out of gas, it's going to slow to a stop. Why don't things keep moving forever? You just told me Newton's law was that they will. Well, if you read it carefully, Newton's law is that objects in motion stay in motion at a constant velocity unless there's an unbalanced external force on them. So on Earth, everything is affected by friction. So nothing keeps going forever. If you push, in this case, you push a box across the floor, you move it that way, there's friction on it. Okay, the box might seem smooth, but on a microscopic level it's rough, and so is the floor, and so they're putting forces on each other. So the unbalanced force from the floor is actually going to slow the box down to a stop. And that's true of everything. There's always friction between every surface, so things don't just keep moving forever on Earth. Now, if you can eliminate friction, then they do. So examples are things in space. In outer space, there's no atmosphere to provide air resistance. There's no friction at all. So if you throw an object in space, it would just keep going forever, at least until it encountered another object or gravity pulled it in. So an example would be the Voyager spacecraft. This was launched in 1977 and it's still going. Because there's no friction out in outer space, it doesn't need fuel to keep it moving at this point. Once, it took fuel to get it launched and get it going and get it away from Earth, but now it's so far, and this thing is out beyond the solar system. It's not near any stars or planets or anything right now. So there's no forces acting on it. There's no gravity pulling it in. Well, for all intents and purposes, there's no gravity pulling on it. There's no friction on it. So it's just going to keep going in a straight line forever until it reaches, something else that'll pull on it. So Newton's first law is easiest to see in a case like that in space where there is no friction. But unfortunately, it's hard to see on Earth because things do slow down, because there is that force that's always working against the motion. Newton's second law is a little more useful in terms of figuring things out because we get to use some math. So Newton's second law explains how changes in motion are related to both the mass of the object and the force acting on it. And we've got these three versions of the formula. So you can see they're all the same. They're all involving acceleration and force and mass. And these are the units that we use. Acceleration is going to be in meters per second squared. Force is in newtons, and mass is in kilograms. So it's the same formula, it's just rearranged three different ways so that we could solve for acceleration, or we could solve for force, or we could solve for mass. Okay, so let's look at some examples of using Newton's second law. So if you have the version of this course with page numbers, it's on page 35, the work it out problems. If you have a newer version of the course, it's actually not going to have the page numbers, but this problem is one of your review problems. So a force in newtons is required to accelerate a body with a mass of 32 kilograms at a rate of 12 meters per second squared. So we just take our formula. Because we're doing force, we want the formula that starts with F equals, and then we just put our numbers in for mass. So our mass was 32, so that goes in for mass, and our acceleration is 12, okay, from over here. And then you just simply multiply 32 times 12. There we go. Our force is 384. So it takes this much force, 384 newtons of force, to make an object with a mass of 32 kilograms accelerate at a rate of 12 meters per second, which is pretty fast. Here's another problem that's just with the rearranged version of the formula. In this case, it asks what is the rate of acceleration. So we want the formula that starts with A equals. Acceleration is force divided by mass. So we plug in our numbers for force. So our force was 20, so that's going to go in for the F. Our mass is 4, that's going to go in for the M. So we have 20 divided by 4. And our final answer then is 5. And our unit for acceleration is meters per second squared. You will run across this. We have questions that ask you to find the amount of force required to stop an object in a certain amount of time. So this is a little more complex. You actually need to do two different calculations to do this, okay? Because we're looking for forces, mass times acceleration, but the question doesn't give us acceleration. It's talking about force and the mass of an object and the time. So you need to do two different calculations to find this. So the first one is going to be to calculate the rate of acceleration. Now this is using a formula that we learned in Lesson 1, Assignment 1. So it's a formula for acceleration, which is just the change in velocity divided by time. So the ending velocity minus the starting velocity divided by time. And remember that often the object is slowing to a stop. In that case, its ending velocity is 0. Okay, or if it's starting from rest, or if it's starting because someone dropped it, or it got pushed off a shelf, something like that, then its starting velocity might be 0. So keep an eye out for that. If it only gives you one velocity, the other one might be a 0. So once we solve for acceleration, now we can put that value into this formula and solve for force. Force is mass times acceleration. So let's look at an example that is from your study unit. A car with a mass of 1,500 kilograms is traveling at a speed of 30 meters per second. What force must be applied to stop the car in 3 seconds? So remember, we can't just jump in to use the Newton's second law equation because we don't know acceleration yet. So first we solve for acceleration. So there's our formula. Acceleration is v2 minus v1 divided by t. So acceleration is our ending velocity of 0 because it slows to a stop, and minus our starting velocity of 30 divided by 3 seconds. So 0 minus 30 is negative 30 divided by 3 seconds, and so acceleration is negative 10. So you say, wait, what's this? Why are these negative numbers? Negatives are scary. No, they're not. It just means it's slowing down. So our acceleration is a negative change in velocity, so that means our acceleration is negative 10. The object slowed down. That's all. So now that we have an acceleration, we can finish the problem. So remember, it didn't ask us anything about acceleration. It's asking us what force might be applied to stop the car. So our force is mass times acceleration. This is our Newton's second law formula. So the mass was found in the problem, 1500. That's going to go here for mass. And the acceleration, well, we just solved for that over here. It's going to be negative 10. So we just put our numbers in, 1500 times negative 10. And our force is 1500. It should actually be negative 1500 because it's working against the direction of motion. So if it was working with the motion and speeding it up, it'd be positive. It's working against it, it's negative. Okay, let's talk about gravity and calculations with gravity. So as you learned back in lesson 1, assignment 1, when we talked about falling bodies, gravity causes everything to accelerate, and it's always at the same rate, which is on Earth is 9.8 meters per second squared. Because it's always the same rate, we can just kind of simplify, and so we use the letter G, a lowercase g, and that replaces A in these formulas. Okay, so the acceleration instead of A is just going to show a G, and when you see a lowercase g in a formula, that number is always going to be 9.8 meters per second squared. Okay, so you're going to see it in formulas where we're measuring weight. You're going to see it in formulas you're talking about falling bodies, and later when we get into talking about the pressure of things underwater, you're going to see it in those formulas too. It doesn't matter what context we're using it in, G is always going to be 9.8. So we just use that to find the force of gravity using a Newton's second law equation. So the original version of the equation is force is mass times acceleration. And now we're just saying force is mass times the acceleration from gravity, which is G. Okay? So what we're actually finding here is the weight. So we're talking about it using, physics language. We're saying it's the force of gravity on the object, but it's the weight. It's the object's weight. So if you know what you weigh, your weight is how much the Earth is pulling on you. It's the force of gravity on your body. So that's what we're calculating. It's just that because we're using metric units, this international system units, we're going to use weight in newtons, not pounds. So you're probably familiar with your weight in pounds, but this is actually measuring it in a unit called newtons. But it's still the same thing. It's how much Earth is pulling down on the body. So here's a couple of examples using this formula. A suitcase has a mass of 20 kilograms. What's the force of gravity acting on it? All right, so we're saying what's the weight of this suitcase? So the force of gravity equals mass times G. So we're going to put in 20 kilograms for mass, and remember G is always 9.8. So we just put those numbers in. Force equals 20 kilograms times 9.8. The unit that goes with 9.8 is meters per second squared. And we just multiply 20 times 9.8, and that gives us 196. So that's the force of gravity on the suitcase. That means the suitcase has a weight of 196 newtons. Another example is we're going to use a different, uh-oh, it's gone. Okay, I think I moved it to another slide. Sorry about that. Okay, here. So G is because of the mass of the Earth. Remember, G is 9.8 on Earth. It actually changes slightly with elevation. So if you're talking about somebody at sea level or at the very top of a very tall mountain several miles high, G is actually going to be a little different. It's not different enough to matter in our calculations, but you do need to know that concept. Okay, so we'll talk about how gravity is affected by distance later, but you need to know the general idea that when you're lower, closer to the center of the earth, G is a little bit higher, and as you go higher up into a mountain, G is a little bit lower. If you're up in an airplane, G is a little bit lower. And we can expand that idea. If you leave Earth, it's going to change a lot. So if you get very, very far away from Earth, it goes away. If you're on a different planet or a moon, gravity is going to be different based on the mass of that planet or moon. So on Earth's moon, the weight of a body is actually 1/6 of the weight of the body on Earth. So you can calculate it the way that your text tells you to calculate in your study unit is you can calculate the weight on Earth and then divide it by 6 to find the weight on the moon. Okay, so let's just look at a quick example. On the moon, what would be the force of gravity acting on an object that has a mass of 7 kilograms? So force is mass times the acceleration due to gravity, so that should actually be a G. It's going to be mass times G. Okay, the A is not wrong, but because it's gravity, we know it's G. So force is 7 times 9.8, and it's 68.6. So that's its weight on Earth. So I'm just going to put Earth. Lovely. And it asks us what the weight is on the moon. So now we divide. We take 68.6, divide it by 6, and there's our answer of the object's weight on the moon, which is 11.43. Okay, and this is what I thought I was showing you before, but I moved it to this slide. You could also take the weight of something and use that to find the mass. Okay, so it's just kind of rearranging the equation, doing it in reverse. Okay, so it's a similar formula. It's still mass and force and gravity. We've just rearranged it. It's still Newton's second law formula. And let's use this example. On Earth, what is the child's mass if the force of gravity on the body is 100 newtons? So we know the weight. We're trying to find the mass. Okay, so we just use our formula. Mass is force of gravity divided by G. It tells us the force of gravity is 100 newtons, and G, as usual, is 9.8. Okay, so 100 divided by 9.8, we get our final answer of 10.2. And that should be labeled kilograms, because mass is kilograms. There we go. All right, so you can take mass, you can find the weight, you could take weight and find the mass. It's just rearranging the formula. Newton's third law, less math, it's that when a body exerts a force on another body, the other body always exerts an equal and opposite force back. Basically, forces always occur in pairs. You can't have a force without a reaction force. So the example of this would be just an object sitting on a table. It has weight. Okay, so in this case, we've got a blue ball here. It weighs 3 newtons. That means gravity's pulling down on it with a weight of 3 newtons. So if you sit it on a table, that means it's pushing down on the table. It pushes on the table with a weight of 3 newtons, or a force of 3 newtons. But the table pushes back on the object with the same force of 3 newtons. And this is true of every force. You can tell because when you put a force on something, you can feel it put a force back on you, okay? If you kick something, let's say you run up to the wall and kick it, it hurts your toe. Why? Because you put force on the wall and it put the same amount of force back on you. If you pull on something, let's say you're trying to pull a heavy sled or something, you can feel it pulling back on you. You know, it hurts. It causes you effort to pull on it because it's putting the same amount of force back on you. So that's Newton's third law. Forces are always in pairs. equal amount of force in opposite directions. Okay, so that sums up Newton's laws and forces, and we're also going to talk about motion in a curved path, okay, which is lesson 1, assignment 3. So objects move in a straight line. This is actually Newton's first law. Remember, objects keep doing what they're doing unless an unbalanced force is applied to them. So something that's moving wants to go in a straight line. It does not want to change direction at all. The force that causes something to move in a circle, that makes that happen, is called a centripetal force. And that force is always directed towards the center of the circle. So let me just bring up that little animation again. Okay, so remember, you need to force something to actually move in a circle. So this object wants to go in a straight line that way, but the centripetal force is what pulls it towards the center and causes it instead to go in a circle. So the object's inertia is what keeps it moving. It keeps it wanting to go outward because it wants to go in a straight line. And then that centripetal force is constantly just pulling it in towards the center. So its inertia wants to make it go out, away from the center, and its centripetal force is pulling it towards the center, and as a result, it just goes in a circle. Okay? There's lots of different centripetal forces. Any object that's moving in a circle has a centripetal force making that happen. So here's some examples. You have supporting force, which is basically just a contact force pushing from the outside. So a roller coaster going around a loop, the centripetal force here is the metal loop pushing on the roller coaster. It keeps it from flying away. Tension, so you've got somebody swinging something around on a string. The tension on the string is just what's keeping it in that circle. If you cut the string, it's going to fly away. Gravity is big, important centripetal force. Okay, it keeps the moon going around the earth, and it keeps the earth going around the sun. We'll talk about that a little more. And friction is a centripetal force. So if you walk in a circle, if you drive in a circle, anything that kind of goes along the ground in a circle is doing that because of friction. So if you drive in a circle or drive around a bend, the friction between the road and the tires is what keeps your car from going off in a circle. So think about it. If you drive around a bend and it's really icy, there's no friction, or there's much less friction. So that's why your car would skid outwards towards the outside of that circle. And let's look at this example of what happens if the force goes away. If the centripetal force goes away, the object just then keeps going in a straight line where its inertia wants it to. So for example, you have the Earth going around the sun because gravity is pulling on it. So the Earth wants to go forward, and it moves forward, and gravity is now pulling in this direction, down. It moves further along its orbit, and gravity is pulling this direction. What would happen if the sun disappeared? Well, that can't happen, but let's just pretend. What if it disappeared? The force of gravity from the sun disappeared. What is the Earth going to do? Well, right now, at this last point here, it was moving in that direction. So it's just going to keep moving in that direction. The sun's gravity isn't pulling it in anymore and making it go in a circle, so it's just going to go off in a straight line. So that's what happens anytime a centripetal force goes away. The object no longer moves in a circle, it goes off in a straight line. And we can actually calculate how much centripetal force we need to do specific circles. So if we have an object and it's got a mass of a certain amount and it's moving at a certain speed and our circle is a certain size, how much force is required to make that happen? And you can also rearrange it and say, okay, we have an object of a certain mass moving at this speed. This is how much force there is. How big will the circle be? So this version of it is to measure the radius of the circle. So in this formula, F is force, specifically the centripetal force, M is mass, V is velocity, and R is the radius of the circle. So let's look at some examples. A car with a mass of 1,500 kilograms moving around a circular curve, velocity and its radius is 100 meters. What will be the centripetal force on the car? So here's our formula: force, mass times velocity squared divided by r, and now we just put our numbers into it. So mass is 1500, so that goes in for m. Our velocity is 16, that goes in here for v. Remember that it's squared, so we have to deal with that first. And our radius is 100 meters, so that goes in there. Okay, so in order of operations, the first thing we do is parentheses, the next thing we do is exponents. Then we multiply and divide. So 16 squared gives us 256. So that's our first step. And then we just solve our problem. So now we have 1500 times 256 divided by 100, and we get our final answer of 3,840 newtons. All right, and we have one more example where we're doing the other way, where we're finding the radius. So this time we're given the mass and the velocity and the force. We already know the centripetal force, and it's asking us what's the radius of the circle. Okay, so we have our formula that's r equals, and then we just put our numbers in. All right, our mass is 1200, our velocity is 20, and our force is 6,000. We take our 20 squared. Okay, remember to do the square thing first. And then our final answer, we take that, multiply it, divide, and then we get our final answer of 80. Right, so this is kind of like the problems before, where the most thought goes into setting it up. What formula do we use? What numbers go where? And then you just do the math once you get your numbers in the right places. The last part of this section is about gravity and Newton's universal law of gravity, and that is that all bodies in the entire universe attract all other bodies. And the force that affects them is based on these things: the masses of the two objects and the distance between them. And this is the equation that you have for it. So this equation, F is the force of gravity. G is a constant. G is called the gravitational constant. And notice this is a capital G, not a lowercase g. Lowercase g is always 9.8, but this is a capital G. It's the universal constant for gravity. And the number for it is always going to be 6.673 times 10 to the negative 11th. Okay? Whenever you see that, that's just the number that you're going to put into the problem, 6.673 times 10 to the negative 11th. And then we take the mass of the first object times the mass of the second object divided by the distance between them. Okay, so I don't think you actually have any practice problems using this formula, but you definitely do need to know the ideas behind the formula, okay, so the concepts that explain how it works. So the gravitational force is directly proportional to the products of the masses. So what do we mean, products of the masses? So products means we multiply. So remember back on this one, you have the gravitational constant times mass of number 1 times mass times number 2 divided by r. So we're multiplying the masses. So if the two masses increase, the force between them will increase. Right? So the gravity between two very large objects is stronger than the gravity between two smaller objects. Okay? So you get two small objects, a little bit of force, larger objects, more force. Okay? But the gravitational force is inversely proportional to the distance between the bodies. So if you get them farther apart, if the distance between them increases, the force will decrease. So over here, they're close together, and we've got our force. If you make them farther apart, our force gets smaller. And that's pretty much it for universal gravitation. So that's all we have for Lesson 1, Assignment 2, and Assignment 3. If you have more questions on these, you can definitely get help from an instructor. And definitely check out our other webinars that we have recorded. We've got some other parts of Lesson 1 and definitely the other lessons for physical science.